Start with interpretation of correlation, bit about correlation causality, and learn a bit about having correlation, perfect correlation or no correlation, and some of the other weaknesses related to um, presence of outlier, having restricted data, and so on and so forth. So, these are some of the things we will discuss in this lecture. So, what is a correlation? Basically, it is some sort of a quantitative measure of relationship between two variables. It has to be interpreted in a proper manner, because sometimes it is perceived as a causation. That is not true actually, right? And we will see actually how it is different from causality actually. The thing is that correlation can very well be computed using the formula, correlation formula, but you cannot interpret without having the proper scatter plot of that. So, scatter plot is very important to interpret correlation value. So, here is this example. So, you see there seems to be a perfect correlation, negative correlation, perfect correlation, right. The correlation coefficient is 0.9. So, that is almost like perfect correlation, right, between these two variables. And then here is this data where you seem to have no correlation. The correlation coefficient is just 0.1%, 0.1. So, that is very, very low, right. So, no, seems to be no relationship, and here you see a somewhat moderate relationship. You have correlation coefficient at 0.72. So, that is not perfect correlation, but also not no correlation. So, it is somewhere in between. So, that is yeah, a moderate level of correlation. Now, so let us learn about Anscombe's quartet. Quartet is about 4, right, 4 variables. So, this was example, an initial example that he took actually to demonstrate this issue in the correlation analysis. So, here you have x1, x2, there are 4 sets of x and y variables, x1, y1, x2, y2, x3, y3, x4, y4. These are some of the things that we have seen, right, in the plots that we just saw in the 4 plots. Interesting thing is that, and you have some 11 observations. So, why 11? Because that was basically, in his example he took 11 such observations, and what he really showed that in this 4 combination of variables x y, you see that the mean of each y variable is 7.5, the mean of each x variable is 9, the variance is about 11 for x, and for y it is 4.13, and the correlation is 0.82. So, correlation between each x y combination, that means x1, y1, x2, y2 and all. So, for each it is 0.82, that means correlation is same, mean is same for each x and each y. And more interestingly, if you actually fit a linear regression line for x1, y1 or x2, y2, each of these 4 combination, you will get this equation exactly like this, y hat equal to 0.5x plus 3. That means, even though we saw, right, in the previous graphs, even though we see completely different distribution of data, you still get the best fit line, you still get the same correlation. So, it is showing actually how important it is to interpret your regression or correlation analysis um, with the help of visualization or visual plots. It is so important, right, because sometimes, very rare situation, obviously not always, in some rare situation it could give completely misleading results. And here you see, right, here you see completely different distribution, but same summary statistics, same correlation, same regression line, and that could give wrong interpretation if you do not take these plots or graphs into account. A bit about correlation and causality. This is a very common thing. So, when you learn correlation analysis, the first thing actually taught to people that correlation is not causation. That means, two variables may be correlated, there may be a strong correlation coefficient between them, but that does not mean one causes the other. That need not be true. Sometimes it is true, sometimes it is not true, and there are many such examples, right. I mean, if you do a bit of a Google search about spurious correlation, you will find many such weird examples, where, one such example is correlation between number of fire trucks sent to the fire and the dollar damage done by the fire. There is a strong correlation, but there is no causality at all, right. It makes no sense to think that there is is a causality. So there's many such examples where you find strong correlation, but there is no causation there. Perfect correlation, right? Um, Two variables may be highly correlated, but they may not have a strong causality also. So that could also be a situation. And then zero correlation. So when you see a correlation coefficient of 0, a correlation coefficient taking a value of 0, sometimes people conclude that there is no correlation between two variables. That's not true. That's not always true. Many times the correlation is actually nonlinear, and when you use a Pearson correlation measure, that does not quantify, or that does not measure the non-linear relationship. It only measures the linear relationship, and sometimes there is no relationship, but there is non-linear relationship which is not captured here. Hence, there is a relationship even though the correlation coefficient takes a value of 0. So that is something to keep in mind, and hence important to build a scatter plot. And then combining populations. So what happens is that if you combine populations, for example, you have two sets of variables which are highly correlated, another sets of variables highly correlated, you combine them, there may not exist correlation. People assume that there will be correlation, but it is not true always. Then restriction of range, and this is a typical problem called the truncation of data, right, or sparse data in some cases, where you, for example, this is a good example actually. You have GRE score and the IQ level or something like that, or GRE score or employability, right. But the problem is that in such a data there are many people who are excluded from this sample, because a lot of people having low GRE score were not admitted to the university, hence their data is not available. So when you do a correlation plot for them, it could give a misleading result. So if you were to include all these extra cases, the ones which are not part of the sample, then you could get a completely different correlation statistic. So that's something to keep in mind. And that there's something called third variable fallacy, which means that if two variables are highly correlated with a third variable, it is assumed that these two variables are highly correlated among themselves. That need not always be true. It could be true many times, but it need not be true. So you can't assume that, you cannot infer that from it. It has to be properly checked, right. Just because x1 y are highly correlated with g does not mean that x and y are highly correlated among themselves. So that's something to keep in mind. So these are some of the issues, and in the context of this particular analysis, I thought giving a bit overview of some of the issues that you